In the previous waves section, this is going to be the bit on diffraction, where we're actually going to split up the spectra and look at the differences depending upon the opening size versus the frequency wavelength that are coming into us, right? Essentially, we're going to be looking at what is happening as we take different colors of light and we pass them through a single slit. Remember what we said is we took the back of a microscope slide, we spray painted it with black paint, took a razor blade and made a slit down it. Okay, and then we passed the light through it. But we just need to back step on one element of this before we get into it. We said, right, remember we said before the amount of diffraction, okay? I'm just going to put it over here like this, and we say amount, okay, was proportional to, if you remember, the wavelength, lambda. Wavelength. And it was also to the width of the slit or the opening. Okay. That's what we said. We didn't quantify it previously. What we now need to do is we need to quantify this. Say, well, how much can we do it? Remember we said if we had an opening wide and a wave coming in here, and we'd got that kind of thing happening there like that, right? We had Huygens principle with the little wavelets coming around the side there. That's what gave us this going around the side. Then what did we do? We made the aperture slightly smaller, and we noticed that we got different wave shapes. We got, in fact, it bent more, right? There's a maximum that we can actually bend it, right? That is, can you imagine if we said that the wavelength and the width of the opening are the same, right? Now, obviously for light, that's a bit of a difficult problem. Yes, I mean, we know that the wavelengths of light, for example, red light is 650 nanometers. 650 nanometers, which is 650 times 10 to the minus 9 meters. Nano, 9. Okay, it's just one way of remembering it. Now, that's pretty small as to make an opening that size. However, in molecular terms, we can find that. So yes, we can find a way of actually having that wavelength in terms of the size, could be between molecules, let's say. So if we passed it between, we technically could have a row of atoms down there and over there, and we've got a slit which is going to be one wavelength wide. All right? But now, let's have a look and see what happens, or rather, let's first just develop and show you this formula, right? What it is this. Sine theta is equal to n lambda divided by a. Now, this is, it was in the syllabus, I'm not sure if it's still in or not, but it does show us what's happening and why. Why the blue light and the red light are different. And it's kind of important that we understand that. So what do we say? What does this mean? Let's diagrammatize it. Let's take here we go. Here's my slit over there. So my light is coming in this way, right? And I'm going to put a screen over here, right? You know that, let's just call that some distance away. Now, as the light comes in over here, remember, we got patterns. I'm going to just put it in let's put it into red, shall we? All right. We got right opposite here, we got bright, right? We got a bright section. Then we went to dark, then we got another bright section, then we went to dark, then bright section, dark, right? So in between here, right, let's just draw a line. It's okay. Can you see that there's a small angle formed there, right? This was the interference pattern, wasn't it? Over here, we got constructive, and over there, we got destructive interference, right? That was where the two waves had got together and made a bright section, and next to it, the two waves had got together and cancelled it out, right? So that's what we had. Now, in this formula here, the width of the aperture is A. So let's put that down. Is the width of aperture, opening, the slit, whatever you want to call it. But that's what it's saying, right? Now, the lambda is the wavelength, okay, of the light coming in. Like we said, there we go. This one here is for red light. Okay, let's put it in as red. Right. So that's, and the n. What is the n? Well, the n is actually, this is -1. The corresponding one on the other side would be +1. It is the amount of, it is the number, the order number of the pattern that you want to get to. So for our purposes, I'm just going to leave n out essentially, and I'm going to just be calling it 1 because this is my angle here, theta. Can you see that it's the amount of bend, isn't it? It's the amount of diffraction that is caused by that opening of slit, size A. So let's look at an example here, right? Let us take red, right? And we know lambda is going to be equal to 650 nanometers times 10 to the -9 meters. All right, and let's take blue light over here like this, and blue. Right, the blue light is going to be wavelength equal to 475, like that. All right. Now, let's say we've got a diffraction slit, and let's put the width of the slit as, well, let's think of one. What would be suitable, right? Let's put the width of the slit as 0.01 millimeter. Okay, that's A. Now we have to change that to meters, don't we? So we're going to take 0.01 divided by 1,000. 0.01 divided by 1,000 is going to be equal to 1 times 10 to the -5 meters, right? Now let's see what happens when we put into that. Sine theta is going to be, we've got here lambda, which is the wavelength, 650 times 10 to the -9, divided by 1 times 10 to the -5. Let's see what we get. 650 to the -9, what's that? That comes to 0.065. And now how do we find theta? We take the arc sine of 0.065. So let's have a look. Shift sine 0.065 is going to be equal to 3.72 degrees. Okay? Well, now let's have a look what happens with blue light, shall we? Let's go to blue. Let's put it in here. Sine theta is equal to wavelength 475 times 10 to the -9 divided by 1 times 10 to the -5. And without going through the whole thingy, let's see what happens to there. So 475 10 to the minus 9 is that, divided by 1, 10 to the minus 5 equals that. 19 over 400, so we need the arc sine of 19 over 400 is going to be 2.72 degrees. Okay. Now, what does it mean? Let's if we had to draw that, for argument's sake, right? What would we have to do? We would have the red light, right? Let's take it in red here, all right? We would have the red light diffract at an angle, all right, from our slit, black. Let's put it here, right? And 1, 2, 3, 4. I don't know. Let's just go there. Put in the middle one here. I'm exaggerating now, obviously, right? Can you see that the red is now at 3.72 degrees? That's I'm trying to squeeze it into the corner there. So let's call it 3.72 degrees. Is that right? So I've got my band here, and over there I've got my darkness there, right? Now, you can see that this is shifted away. But if we draw the blue one, right? Blue, no, I needed black first, all right? Okay, like so. Now we're going to draw the blue. Remember, we've got our central blue band there. Now I'm going to be drawing it at 2.72. At 2.72 degrees, which means that my blue light isn't going to be diffracted. It's not going to be bent as much, is it? It's going to, my red pattern, my interference pattern, is going to spread out. My blue is going to be closer and narrower. All right. You'll see on some of the patterns, if you go and look up some of them, I mean, we're putting a few in to show you, but if you look at them, you'll see that they're actually quite marked, the difference. It looks obviously bigger than it is, but by making that gap smaller, right, we can increase it, or the wavelength is going to change it, isn't it? Now, essentially what that's showing us is it's showing us why we get a difference between the red and the blue light, okay? It comes down to this formula here, doesn't it? It comes all the way back to this formula here, and I can use this one here. Okay. Remember, the N over there is actually to my first fringe on the outside. Okay, so that kind of puts together what happens when we do the different colors of light through the single slit. And yes, you get double slit experiments, you get diffraction grating experiments, which essentially do the same thing, okay? But I just wanted to show you from a theoretical base what's actually happening out there, as opposed to something that's not based in theory and where you have to do it. So you can see that the wavelength, right, is playing a role there. It is the blue wavelength and the red wavelength, right? And the shorter the wavelength, the tighter around the central, let's say the central strip it becomes. Okay. So we're going to move on now into the physics, and we're going to tackle the next sections, which is going to start looking at the electrostatics, building up towards electronics, building up towards circuits and things like that. And once again, you'll see that we'll start to develop a series of how do you do these? What is the recipe for it? What do I do A? What do I do B? What do I do C?